Okay. Hello friends, this is Professor Rahul Krishnaji Bhavne, and in the subject of heat transfer, today we will see experiment to determination of thermal conductivity of metal rod. So this is yeah, our practical content. So let us see. So determination of thermal conductivity of metal rod. This is your write-up which I will provide later on. So title is to determine that is determination of thermal conductivity of a metal rod, and this time whatever be the metal rod is there, that is made up of copper. So this is a little bit theoretical portion, theory behind this experiment, and one table is there for some metals, pure copper, brass, steel and stainless steel. What are their standard thermal conductivity? Especially for pure copper, it is 390, and this thermal conductivity is measured at 20 degrees centigrade. If we go with a metal, especially metals, so we observe that as we increase the temperatures, that means if we heated the metals, then its thermal conductivity decreases, and most of the cases this is happened. So in especially metals, if we increase the temperature and measure its thermal conductivity, so we observe that thermal conductivity of metals decreases. So if I go for pure copper, this is a 390 watt per meter Kelvin at 20 degrees centigrade. If suppose I heated this copper to 40 degrees centigrade, so thermal conductivity will be lesser than this 390. Why this happen? Because thermal, that is heat transfer in metals, especially following two phenomena. One is by transport of free electrons, migration from hot end to cold end, and second criteria or phenomena is the lattice vibration. Now when I heated any metal, so that lattice vibration become so strong that it restrict the transport of free electrons. And in metals conduction, uh, heat majorly transfer by the transport of free electrons, but when we heated it, the lattice vibration is so strong, they provide abstraction to transport of free electrons, so thermal conductivity get decreases. So remember this point, many time it is asked in practical exam, why in particularly metal, when we go with a higher temperature, thermal conductivity shows decrease. Okay. So this is our schematic. What is the arrangement inside that experimental setup? So this kind of arrangement is there. There is one copper rod, and one end the copper rod is provided with a electrical heater where we maintain voltage and corresponding current. So we supply heat here at this end. Then this copper rod is covered with some thermal insulation in a box, cylindrical box kind of container, and this container test length is of 200 mm. So whatever be the thermocouple we mounted on the rod, it is within this 200 mm rod. This is our test length of metal rod. And from heater side, thermocouples are attached exactly at a 2 centimeter difference. So first thermocouple T1, T2, T3 up to T9. So total T9. So 9 thermocouples are mounted on the rod. And second end. So first end it is inserted to the heater coil. Second end it is inserted into the water bath where we supply cooling water, and we maintain a particular flow with the help of knobs. So cooling water continuously entering from one end and leaving from the second end, and during its path, when heat reach to the second end, so this cooling water extract the heat and remove out. So first end we provide heating, second end we provide cooling. So heat will travel from heater to cooler end, and we must calculate all the readings after steady state. Imagine when we start the heater, so heat will start moving from this heating end to cooling end. So first it will reach to the position T1, then later on then T2, T3, T4. Likewise, when it reach to T9, then after it will reach to cooling end, and when heat reach to cooling end, then circulating water carried out that heat. And meanwhile, whatever be the length, test length 200 mm, this rod is completely covered with insulating powder, so it is assumed that is radial heat loss is zero. But in actual that is not the case, because no system can be a perfect insulating system. Okay, so T10 is the water inlet temperature and T11 is the water outlet temperature. So likewise we have to monitor our supply voltage and current. Then we have to measure the temperatures T1 to T11. Okay, and in addition to this we have to maintain the water flow also, most probably 300 to 400 ml per minute. This much must be the water flow. If we increase the water flow, then it will be undercooling, so this should not be there. So take a precaution whenever we conduct this experiment. So maintain the water flow 300 to 400 ml per minute. Okay, so this is the experimental setup. Safety precautions. So whenever we start any equipment, always check thermostat at zero position and then only switch on. Procedure, as I just said, we have to start electrical supply to the heater. Then with the help of thermostat, we will maintain a particular voltage and corresponding current. So accordingly, heat will supply. Then we have to maintain a cooling water flow rate, and we have to wait for steady state. That means about 20 to 30 minutes should be there before taking first reading. And likewise, we have to note down a few readings. Then we will make an average of that and then go for a calculation part. Observations. So material is a copper material, so there is a copper rod. Length of that total rod is 350 mm, but our test length is a 200 mm. Why 200? Because the previous end is inserted into the heater and second end is inserted into the cooling path. So test length is a 200 mm. Diameter of that metal rod is 25 mm. Specific heat of water, it is given 4.187 kilojoule per kg Kelvin. Input voltage we have to write down here. Input current, corresponding current we have to write down here. And flow of cooling water, the most important parameter, we have to maintain here. And as I said, it must be in between 300 to 400 ml per second. Okay, so 0.3 to 0.4 liter per second. Now this will be our observation table. So after 10 minutes, 20, 30, 40, but this first reading, that means it is written here 10 minutes, but actually this is the first reading which must be taken after starting your equipment and setting the voltage, about 20 to 30 minutes. So that is our warm-up period for that equipment. So first reading should be after 20 to 30 minutes. Then after each 10 minutes interval, we will note down, and we are going to note down only temperatures. Okay. Once we have voltage, set voltage and current, then only we have to note down the temperatures from T1 to T9, which are the temperatures for rods, and T10 and T11. So here must be T11. So T11 are the temperatures on cooling circulating water. So T10 is the inlet water, T11 is the outlet water temperature. Now the calculation parts. So cooling water mass flow rate. So as we know that 1 liter is equals to 1 kg of water, especially water. For different fluids it might be vary, but for water it is same. So we have to maintain about 300 to 400 ml per minute supply. So whatever you maintain, you must write here. Okay. For this particular experiment, I maintain 300 liter, sorry, 0.3 liter per second. So accordingly, it will be 0.3 kg per second. That is the mass flow rate of water. Then heat gain by cooling water. So how much is the heat gain by that circulating water? Actually, heat supplied is different. Heat supplied with the help of electrical current. So power, product of voltage and current is the heat supplied. But from heat supplied to cooling end, whatever be the heat travel, and after steady state it is extracted by cooling water, that much amount of heat is actually transferred through that rod. So heat gain by cooling water is the heat transfer through that rod. So Q is equals to mass of water, Cp of water, and temperature difference of water. So T11 outlet temperature of water minus T10 inlet temperature of water. So this much amount of heat is actually travel through that rod. So in this particular experiment, don't consider Q is equals to V into I. That is the total heat supplied. Q is equals to the heat extracted or heat gained by the cooling water. So MCP delta T. Next, thermal conductivity of metal rod. There are many kind of experimental setups are there where we divided that metal rod into 3 segment, first, second, third at different distance, and accordingly we get the different values for K. But in our experiment setup, it is a very simple experiment setup, so we don't make it any kind of divisions there. So in our, as per our setup, we will calculate thermal conductivity of metal rod by using Fourier's law of heat conduction, that is Q is equals to Ka dt by dx. Thermal conductivity, we are interested to find out this. Q we already calculated from the heat gain by cooling water. Area, so cross sectional area, so diameter is provided, so we can find out the cross section area by pi by 4 d square. Dx, so what is the length? So length is a test length, and test length is 200 mm, so it is 0.2 meter. Now what is dt? So dt is the temperature difference, T9 minus T1. But as here we don't consider a minus sign, so when we put the value of dt, so it must be T1 minus T9, because T1 is nearer to heater, T9 is nearer to cooling. So here we are not taking a minus sign in Fourier's equation, so we will take a dt as T1 minus T9. So Q value is known, A value is known, dt is known, dx is known, so we directly find the value of K. So in a result, we have to write 3 datas. First, cooling water flow rate, because if we increase the cooling water, then it will definitely affect the heat transfer rate. Then heat loss from the metal rod, that is Q value, and thermal conductivity of metal rods. And in last, we have to draw a graph, and in graph we have to take a temperature on y-axis and length of that rod on x-axis. But the length, consider the length of test length only, not the total rod length. So this is the video clips. This is our experiment, thermal conductivity of metal rod, and this is the cooling water jacket, and this box is the actual covering for insulated portion of test length. We have to maintain a cooling water supply. So this is cooling water inlet. With the help of this knob, we can maintain the supply. and this cooling water thermocouple, inlet thermocouple. Water will circulate this jacket and coming out, and this is the thermocouple to water outlet temperature, and the water outlet we directly put into the drainage. This is a voltmeter, then temperature knob, ammeter. This is the on-off switch and dimmer stand. So switch on equipment, then with the help of dimmer stat, maintain the voltage. Here also in this experiment, we are going to maintain 100 volt. And remember, always use the dimmer stat very slowly. Okay. So 100 volt and corresponding current 0.368, and these are the temperatures. So as just we started equipment, so all thermocouples nearby same temperature range. So we have to wait for 20 to 30 minutes so that there will be a change, because heat required time to travel from heating end to cooling end. There are T11, so if you go for a T12 position, so there will be no reading. Now outlet. Now the outlet is put in a beaker, calibrated beaker, and with the help of a knob, we have to maintain a flow rate. So it is just like a trial and error method. For a 1 minute, 300 to 400 ml water should be there. Not less than 300 ml or more than 400 ml. So for this particular experiment, I maintain a 300 ml. So I note down the time on stopper, how much time is required to fill the 300 ml, and that will be our flow rate of water. So after maintaining water flow, we have to let this equipment for 20 to 30. And once your measurement is over, then put that drainage pipe into the outlet. So this is our experimental setup. Now the last reading which I note down here, because before that, after a 10-minute interval, once it get steady state condition, so I note down readings, and the last reading I shoot a video clip here. So this is T1. Many times the reading is fluctuating, never get a steady. So when it note down, so note down that particular reading which is repeatedly coming as and appearing just like a 61.1. So it is repeatedly coming. So for this particular position, it is not a steady. So we will use T1 as the 61.1, then T2. Now it is steady 59.3. 59. So many times it happens that your reading does not show a steady condition. So in that particular case, we have to note down the frequently showing reading as our final reading. This is a T10. T11 35. If trying for T12, so there will be no reading. So this is the last set of readings. And when I make a table, so T1 to T11, water flow rate is 300, voltage is 100, current 371. This is the final, okay. When we set a voltage, then it will be a different value for current, but when that conductor get heated, so automatically current value will change. So when you take a last reading, that time note down what is the voltage and current, and these are the various temperatures. So this is the last set of temperature which I recorded on a video clip. Then I make a average of all these, and by using this average value I will calculate everything. Remember, in the first slide it is showing that for pure copper it is 319 watt per meter Kelvin, that is thermal conductivity. But same value it will not be shown on our experimental setup because it is conducted under non-standard condition. Secondly, that copper rod, we don't know the exact purity of that copper rod, and 390, that thermal conductivity for pure copper rod, it is exactly at 20 degrees centigrade. Okay, if I increasing temperature, so definitely it shows a lesser value. But this copper rod under non-standard condition, we get the value nearby 390, not exactly 390. Okay, but it must be in the range of that 390. So thank you friends, calculate, complete your